Yeah, let's look. So we'll be going through why 360-degree video encoding is expensive. Then we're looking into fast multi-rate encoding basics. Then why cube map projection is useful in this case. And I'll also explain about the reuse strategies and the experimental results. And finally, the summary and the future work. So 360-degree video is used widely used in VR streaming and immersive applications. This requires very high resolution and high frame rates and uses special projections. This makes encoding quite expensive. So if you need a very great VR experience, it comes with heavy computation. Uh, So videos are encoded at, in adaptive streaming, videos are encoded at multiple, uh, yeah, so.
Use this one.
Yeah. Sorry about that. So in adaptive streaming, videos are encoded at multiple bit rates. So in 360-degree video, we use viewport adaptive streaming. So here, only the user's current viewport is at high quality. So this leads to many representations and high encoding costs. So encoding a single 8K 360-degree video can take hours together, and this cost quickly increases when we have many resolutions to be there and also many bit rates versions. So fast multi-rate encoding is necessary for scalable VR streaming. Let's look into the fast multi-rate encoding basics. So when you encode a video, the frame is divided into CTUs, which is coding tree units, and the coding tree units are divided into CUs, coding units. Then the CUs are divided into PUs and TUs, which are the prediction units and transform units. So the encoder does many computationally heavy work here. So in fast multi-rate encoding, what happens is the encoding analysis which you got in the previous encode is reused by the next one. So this avoids the recomputing everything again and again. There are two major paradigms here. The first one is a top-down paradigm, where the decisions which are taken at the highest resolution, highest quality representation is uh, given to the lower qualities. So this delivers a strong rate distortion performance, but it's limited speed up. And the second one is a bottom-up paradigm, where you have the fastest representation encoded, and all the encoding analysis is given to the higher representation. So this allows us to have a high concurrency, and the scalability is suitable for VR streaming. So in our framework here, we'll be considering the bottom-up paradigm. Let's look into the different formats which we have taken into consideration. The first one is ERP, equirectangular projection. So you can notice that there are strong distortions at the poles here. It has weak consistency and it's harder to reuse. And we have cube map projection, which has a lower distortion, and it is divided into different phases, and each phase can be encoded in parallel. So it supports massive concurrency. So it's better suited for fast multi-rate pipelines. Let's look into the proposed reuse strategies here. So in fast multi-rate encoding, the one we are discussing about is right now is the one in dotted lines. So in fast multi-rate encoding, each phase is encoded. We do a full RDO there, that's rate distortion optimization on it. And the analysis which we get, the block partitioning and the prediction modes, these are given to all the dependent encodes, and this leads to reducing the encoding time, and only a minimal refinement needs to be done on the following encodes. And this particular image here, this is specific to CMP. So what happens in our framework, we are evaluating both ERP and CMP. And in CMP, we have a 360-degree video. We convert it into a ERP video to CMP using the Samsung 360-degree tools. And each phase is encoded using fast multi-rate encoding. And in ERP, we wouldn't have the the conversion part and the CMP format. It would be directly processed in the fast multi-rate encoding module. So the benefits in CMP would be it can be parallelized and it becomes faster. So there are two strategies which we are considering here, which is the cascaded resolution chain. So what happens here is that we have a HD anchor, and the anchor is used to accelerate the HD dependence, the 4K dependence, and the 4K anchor. And the 4K anchor is used to accelerate the 8K anchor and the 8K dependence. So here, the memory footprint would be minimal. It would be N-1 analysis files. And in per resolution anchoring, we have the HD anchor, then you have the HD dependence and 4K anchor being accelerated using that. And you have the 4K anchor used to accelerate 4K dependence and 8K anchor. And finally, the 8K dependence are accelerated using the analysis from 8K anchor. So let's look into the experimental results. First, we have the experimental setup. So we use the SJTU 8K 360 data set, which has 15 sequences over HD, 4K, and 8K, and multiple quantization parameters. We have also analyzed the data set in order to make sure that it has good variety to support this. And we have used the X265 analysis sharing setup, which allows you to, we use a load reuse level of 10, which means that we use the entire analysis. Then we say refine intra 4, which means that for the intra frames, we do not reuse the analysis. Instead, we do the analysis again. And for we use refine inter 2 and refine MV1. So this is something which is already supported by X265, the analysis sharing setup. And the quality is calculated using PSNR and WSPSNR. WSPSNR is better suited for 360-degree videos, and the encoding efficiency is being calculated using Jondegaard Delta, PSNR, and WSPSNR, and also the encoding time is being reported. Now let's look into the results. This is like a huge table, so I wouldn't bore you with the entire details. You can look it up in the full paper which has been submitted. And what I would like to point out is that using the framework suggested, we had a 50% reduction in encoding time with a 0.77 dB increase in WS-PSNR. And WS-PSNR is a better suited for 360-degree perceptual quality. And the largest deviations were in PRA from more aggressive reuse. So let's look into the summary and future work. So we introduced a fast multi-rate encoding framework for CubeMac 360 video compliant with OMAF streaming. And we've achieved a encoding times reduction of 50% and 4.2 times speed up, which almost enables near real-time via streaming. And the plans for the future would be to extend this framework to VVC pipelines or integrate machine learning and combine encoder and decoder enhancements there. So that's all from my end. Thanks for your attention, and open to any.